Touching the mic, everybody. So last class we talked about the experimental study of photoelectric effect, and now what I'm going to do is last time when we studied this experiment, we found that the nature of light doesn't behave like a wave. Instead, the light behave like a particle, right? So this is what we have done so far, and then we have done a 4 graph which was not able to explain using a light as a wave nature, right? So what I'm going to do now is now we know very well that light has wave nature. All right, light is in wave nature. Light is wave in a way. I say light is wave. And we come across so many phenomena, right? So like the end of 19th century, the scientists, the physicists confirmed that light has wave nature, right? Like so many phenomena such as interference and diffractions, polarizations, all these phenomena tells that light has wave natures, all right? I mean, electromagnetic light is electromagnetic wave. And we talk about this that Maxwell equation explains the electromagnetic waves, everything we talk about, right? So in a way we say that light, now it is very well established that light has wave nature, right? All the wave aspect, right? Like wave phenomena, light could able to explain, right? So this is what we have done. Even in chapter number 9 we talk about interference, diffractions and polarizations, right? These all are the wave phenomena, right? Now the point is that light, now all the phenomena that come across with light does not able to explain by a wave nature of light, right? So the experimental study, right, the photoelectric effect is one such example, right? And we have come across something called quantum effect, right? Maybe later you will study. This is again, if I bring a light as a wave nature, we won't be able to explain the photoelectric effect. Alright, we won't be able to explain a photo. So therefore, we need another idea, right? We need another idea to explain that particular phenomena, right? So therefore, it is best if we could assume that light has particle nature, right? And such an idea was first studied by Max Planck in year 1900, and then the photoelectric effect, the phenomenon called a photoelectric effect was observed by so many scientists. We have done last time, and the best explanations was first given by Albert Einstein in year 1905, right? So Albert Einstein's brought radically new ideas about light, right? Nobody thought about that particular idea, right? People believe that light has wave nature, and people never knew that light has particle nature. But however, Albert Einstein explained that observing all the graphs or the experiment, right? He found that light behave like a particle nature. So when I say light behave like a particle nature, I mean light is a discrete in nature, right? And it was Max Planck who talked about the quanta, right? Quanta, that means the energy package of light, right? So he used that concept and tried to explain photoelectric effect, right? So in year 1905, Albert Einstein proposed what we call as and able to explain what we know as photoelectric effect. Alright, so now just going through different observations and then how he explained those observations using light as a particle, right? And we won't be able to explain those observations using light as a wave nature, right? So the first is that photoelectric emissions. So let's say when I say light is a wave nature. If light has a wave nature, when a light interacts, if it is wave, then it is continuous. Alright? Then there is a continuous. If light falls on an object, if light falls on the matters, the continuous absorption of light taking place by a matter, right? So however, when we study a photoelectric effect, the photoelectric emission does not take place a continuous absorption of energy from radiations. All right. So that means the light, the electron coming out from a metal surface is not continuous, right? This is of a discrete forms. All right. And this electron takes discrete energy and then electron comes out. All right, so detail we'll study now, right? Later, right? And then Einstein said that he talked about the radiant energies. He says that radiant energy when a light interact with the matter is not a continuous form. It is not a continuous form. It is of a discrete form and it has a discrete unit, right? And this is what we what he called as a pointer of energy. This is what he called as pointer of radiation of energies. And he says that, and that 1 pointer of radiation energy, this 1 pointer of radiation energy, so he says that 1 pointer of radiation energy means this is this much, right? So that means, he says that light is not the way light falls, when light falls on a matter or a metal surface, the interaction of a matters and a light is not in a continuous forms, it is of a discrete. The matter takes a discrete energy, right? And how much that energy is? That this is the energy. That means each light. So we can say it is a stream of light falling on a metal surface, and each stream of light, each particular stream of light has energy this much. That is E is equal to h nu, and h is what we call as a Planck constant. H is what we call as a Planck constant. So this first idea was brought by a Planck, and so therefore the constant is what we call as a Planck constant. So, and each radiant energy has this much energy. This is mu is a frequency. This is what we call as a frequency. This is what we call frequency of light. So this is what red has a particular discrete energy. And the violet has a particular discrete energy, blue has a particular discrete energy. That's the point, right? So we say that the quantum of energy of radiation has this much energy, right? So electron takes this much amount of energy at a time, all right? When a light goes on falling or keep falling on a metal surface, means each time electron receive this much amount of energy, all right? And then we say that an electron absorb a quantum of energy, that means the quantum of radiations, right? This much amount of radiations. Alright. So now look at here. We know that electrons are bound to a nucleus. If I have a metal surface like this, electrons are bound to a metal surface. And we talk about work functions, right? The work function is minimum amount of energy required to remove electron from metal surface. Alright. So therefore, let's say a work function is phi naught. Now the light energy, the discrete light energy, right? When a light falls on a metal surface, this provides a discrete energy, right? And if I say if an amount of energy of a light, that discrete energy, if an amount of discrete energy is more than a work function. Alright, that means if that amount of energy is more than work functions, that means that amount of energy could able to pick up or remove electron from metal surface and then start moving with some kinetic energies, and that is what we call as a maximum kinetic energy, right? So this is what we call as a maximum kinetic energy. Alright, so this is the point. The electron is emitted with the maximum kinetic energy emitted is given by source. So therefore, what I would like to tell you is, this is an amount of energy each light has. This is the amount of energy each light has. And this much amount of energy is spent on removing electrons. So this much amount of energy is spent on removing electrons. So how much energy is left now? Alright, and this much amount of energy is left. So this is in the form of kinetic energies. this is in form of kinetic, and which we call as a maximum kinetic energy, which we call as maximum kinetic energy. That's what we talk about. So light, we could have Einstein's conceptualize that. Now light, when I send a beam of light, it is not that wave form. It is of a stream of particles. It is a stream of particles, and each particle has energy this much, and each particle is falling on a metal surface, and electrons receive energy from each particles. Electrons receive energy from each particle. So that's the point, right? So this is what we have. And now look at here. Now if I increase the intensity, normally if it is a wave, if it is a very much in the wave nature, if I increase the intensity, the energy has to increase. Alright, energy has to increase. Alright, and more energy could fall on a metal surface, and then electron may come out. Alright, it is not so, right? If you increase the energy, if you increase the intensity, look at here, it is something like this, right? If you increase the intensity, however, if this is less than a work functions, alright, if you go on increasing the intensity, however, if energy of each discrete photons, or energy of each discrete light energy of each light is less than the work functions, no emission take place. No emission take place. Alright, no emission take place. Alright, so this tells that intensity is not that that we visualize in form of a wave. Alright, intensity here refers to a number of light particles falling on a unit area in a unit times. So if I say in 1 second, 1,000 electrons, 1,000 wave light particles are falling on this area, and in next time if I allow 10,000 light particles falling on there, that means intensity is increased. So now the very intensity, the concept called intensity has changed, right? So when I talk about wave, intensity is nothing but amplitude, a square of amplitude. Now when we talk about the photoelectric effect, it is not that. Intensity is number of light particles falling on a unit area in a unit times. So this could be able to explain photoelectric effects. So therefore, no matter how many light particles are falling on a metal surface, if the energy of light particle is less than work functions, no emission take place. So therefore, now we would like to define intensity, right? So that what is the intensity is what we call as a number of photons incidence per seconds. That's the point. So now each light particle is what we call as photon. I would like each light energy is called photons. Or a quantum of energy, or what should I say, a quantum of energy is called photons. Alright, quantum of energy is called photons. Alright, so if I say if intensity increases, number is going to increase. If intensity is increasing, so now look at here. Now if I say as this is more than work functions, then if we increase intensity, let's say if intensity increases, and what we found is we found a photo current increase. We found that photo current increases. So this tells that more photons, more light particles are falling on a metal surface, and more electron receives light energy and then coming out. So that's the point, right? So this is what we have. The maximum kinetic energy or emitted electron is determined by energy of each photon. That's the point. So therefore, this is again I'm writing. So therefore, this is maximum kinetic energy is what we term as h nu minus phi naught. This is what we have. All right. So quantum of energy is what we call as a photon, and each photon has energy. Each photon has energy. Each photon has energy h nu. So therefore, the energy of photon is determined by frequency. Energy of photon is determined by frequency. So therefore, ultraviolet is having higher energies, and the visibles are having less energy, and infrareds are having still less energy. So that's the talk about. So now, when we talk about energy of light, we talk about the frequency. The frequency is the one that determines energy of light particles. And now, in a way, we say that now light has a definite energy. Light has a definite, and light transfer energies. And then I say that, and light has also momentum, right? Light has also momentum, right? So therefore we say that according to Einstein's equations, what is that Einstein equation? This is the Einstein equations. This is Einstein equations. This is Einstein equations. This is Einstein equations. We say that according to Einstein equations, maximum kinetic energy is linearly dependent on a frequency. That's the point. This is a linear equation, right? This is the linear equations. This is linear equations. This is linear equations, and the intensity of radiation is proportional to number of quanta, right? Number of energy quanta. Number of energy quanta, right? If a more energy quanta falls on a metal surface, more electron comes out. All right. Per unit. That's the point. And again we say that the maximum kinetic energy cannot be must be non-negative, right? If I say if energy is more than work function, only then it comes out, so that it is always positive. Then again, which I told you already. And the photo emission is possible only if energy is more than work functions. Only if energy is more than work functions. And then now we define what we call as a threshold frequency, right? Threshold frequency, right? Threshold frequency. We define what we call as threshold frequencies. So what is the work function? So work function can be defined like this, where mu naught is what we call as a threshold frequency. Mu naught is what we call a threshold frequency. So threshold frequency is defined by work function divided by h. Work function divided by h. Work function divided by, and this is what we term as Einstein photoelectric equations. This is what we call as Einstein photoelectric equations. Now look at this diagram. Right? Look at this equation. Look at these equations. And we say that equation is, and I can rewrite these equations. I can rewrite this equation as in these forms. Maximum kinetic energy is also equal to a stopping potential, right? This is what we call as a stopping potential. This is what we call as a stopping potential. All right, this is what we call as a stopping potentials. And then, therefore, I can write this in these forms, and this is now equation, and this is a linear equation, right? This is a linear equation. Again, I say this is linear equations. A linear equation means the stopping potential is linearly proportional to frequency. That means I say a stopping potential is, this is a stopping potential, I will write it BK. Alright, stopping potential is linearly proportional to frequency. Stopping potential is linearly proportional to frequency. Alright, so linearly proportional means now this is S by E. S by E is what we call as a slope. Slope of a linear equation. This is a slope. And this slope remains same. H is a Planck constant, E is a charge. This is the Planck constants. This is the Planck constants. And this is the electron charge of electrons. And this is constants. S by 2 pi is constant. Therefore, irrespective of what metal surface you are using, the slope remains same. So that's again one proof. The slope remains same. In a way, this Einstein photoelectric equation able to explain this graph of this observation, that is graph, right? And what is the slope? Therefore, I just say that this is the slope, and this slope is given by, slope is what we call as H by E. Alright. And then what is this? And this is y intersections. This is a y intersection. I can extend this. And this is the potential. This is the potential. I can write this is the negative potentials. Or I say this is the potential. This is the potential. This is the potential, and this is what we call as threshold frequency. This is what we call as a threshold frequency. These two are what we call as a threshold frequency. So threshold frequencies are different, right? Threshold frequency for metal A, threshold frequency for metal B. So this is what we talk about. So in a way, we could have to explain entire these graphs. So we say that, and then experimentally it was found that the value of H, this is the very important, right? So the experimental value of H is equal to the theoretical value of H. Experimental value of a Planck constant is equal to the theoretical value of Planck. Therefore, Einstein equation is right. So we could say that particular theory is right only under experiment, only by doing experiment. And we have a constant, Planck constant. The Planck constant we obtain from a experiment, and Planck constant we obtain from a theoretical, that means theoretical explanation. And these two values are very close to each other. Then we say that the theory is right. So this is what we call as Einstein photoelectric effects. So again I say that these things are done. So this is what I have written now. Equation, right? This is what we talk about. In Einstein picture, the basic elementary process involves in a photoelectric effect is absorption of, this is very important, right? Absorption of light quantum, alright, by electrons. So electron absorbs a discrete amount of energy, a quantum of energy, and this process is not, process is what we call an instantaneous, right? It's absorbed energy, and then we find instantaneous emission of electron, right? So instantaneous emission of a light is taking place. All right. And then one more is that the intensity of light only determines electrons, right? Only determine how many electrons able to participate. So that means if intensity is higher, then more electron gets the energy, and then electron comes out. That's the point. So this is what we have. Again, this is another graph. I extended it. This is the. Now, what is the significance of minus potentials? Minus potential means the electrons are bound to a nucleus. Electrons are bound to the nucleus. Nucleus attracts electrons. So the electrons are bind to nucleus. So these equations, right? These equations. Look at here. Metal A is more sensitive to light than metal B. Why? Because this frequency is more than frequency 2 is higher than frequency 1, which implies that metal 1 is more sensitive than metal 2. All right, metal 2s. And why more sensitive? Why metal 1 is more sensitive? The binding is less. Potential is less. Negative potential is less. If a negative potential is greater, it is greater bind. So this is what we talk about. So therefore Einsteins could able to explain all the graph, right? All the graphs. So let me show you all the graph, right? Now I will show you this. So as far as this graph is concerned, Einstein says that light is not a continuous. A light is a packet of energy. A light is a discrete, and it has an energy. What we call as each light has this much energy. And having so, if a light, this energy is more than. Under these conditions, if a number of intensity increases, then a photoelectron emission increases. Why? Because more electron receive energy and it comes out. So this is the first graph we could able to explain, right? Okay. So this is and if this is less than, all right, no matter how intense light falls on the metal surface, you won't be able to remove electron from metal surface. All right. So therefore, this is one very important idea. The second is that second also tells about this. The stopping potentials. So stopping potential is not determined by intensity. Intensity determines the number. So stopping potential is all determined by frequencies. So we are going to choose the three different light of a different intensity with same frequency. That means the energy remains same. All right. Energy of a light is not determined by intensity. Intensity is just number falling on a unit area, unit time. So this is the point. So this tells you this, right? This graph also tells you this. So intensity is just number. Frequency is the one that determines energies. All right. Now next. This is how to talk about. So we have three different frequency, right? We have a three different frequency but same intensity. Same intensity means number of electron coming out remains same. However, electron comes out with a different energy. Why? Because different energy of light is falling on a metal surface. If a higher energy light falls on the metal surface, the electron coming out with a greater velocities. If a lower energy falls on the metal surface, energy comes out with a much lower energy, right? So this is what we have. So therefore frequency, the frequency that determines energy of light. It is not the intensity, but it is the frequency that determines energy, right? And then we talk about this. Right? Now metal surface. Different metal surface has a different work functions. Alright, and work function corresponding to what we call as threshold frequencies. Alright, threshold frequency. And what we found is a stopping potential or maximum kinetic energy. We found that the maximum kinetic energy is proportional to frequency. Proportional to frequencies. However, we have a y-interceptions. And what is that y-interceptions? This y-interception is nothing but a potential. Potential we talk about. Alright. So therefore this graph is very well explained by the equation which I have written. This stopping potential is equal to h by 2 pi mu minus phi naught divided by E. This is the stopping potentials. This is the equation that would able to explain this graph. Alright. So in a way, now now we could be able to conceptualize that light is no more a wave when a light interact with the matters. Alright? Yes, light behave like a wave when a light pass through a small narrow slit. Alright? And light behave like a wave when light falls on the obstacles. Alright? However, when a light falls on the metal surface, when a light falls on the metal, light behave like a particles. The way electron comes out from metal surface is exactly light is acting like particle natures. So this is what we call as Einstein photoelectric equations. All right. Now having this, we could be able to tell that light is a particle nature. Light is particle nature when a light interact with the metal surface. When a light interact with the metal surface. So now to tell you, when a light falls on the ice, when we see some things, now light undergo both wave as well as particle natures. When a light pass through our pupil, right? The lens, when a light pass through our lens, light act like a wave. When a light falls on the retina, light behave like a particle. So therefore, when we see something, both the phenomena are taking place, right? First, light acting like a wave. So therefore, we have what we call as resolutions. And then when the light falls on the retina, light act like particles. All right. So this is what we talk about. Okay. So now to summarize, we say that light in interaction of matter with the interaction of radiation with matter, the radiation behave as if it is made of particle called a photon. So this is the point, right? Where do you see light acting like a wave? Where do you see light acting like a particles? When a light interacting with matter or a surface. Alright. And say that each photon has energy this much. So therefore I say that, I told you that light has a definite energy and definite momentums, right? Light has a definite energy. How much energy? H mu. And a definite momentums, right? H mu by c. This is frequency. What we call as a frequency. This is one point. The second point is that all the photon of light of a particular frequency and wavelength has same energies, all right, and same momentum. So that's this equation is telling us. If frequencies are same, light will have the same energy. No matter how much intensity of light is falling on a metal surface. And the momentum transfer, right? The moment light falls on the electrons, the electron gets momentums, right? There is a transfer of momentum taking place. So the momentum of a light energy, the momentum of a light and the energy of a light remains same for all light of a particular frequencies. Same frequency, same momentum and same energy. So this is it. However, intensity is that there is only an increasing number of photon per seconds crossing a given area. That is, if you could able to increase intensity, it is a number that is increasing. So therefore, the energy of a photon is independent of what we call as intensities. Now the point is, the photons are electrically neutrals and are not deflected by electric and magnetic field. This is again one very important property of light. And then one more I would like to tell you is the collision, right? When a light falls on a metal surface, it is something like if I have a billiard ball striking with another billiard ball. So that how the momentum transfer is taking place. Same phenomena are taking place even in light. When a light falls on the metal surface, electrons are kicked out. So there is a transfer of momentum taking place from light to electron taking place. That is why electron coming out with some momentum, right? So the total energy and the total momentum are conserved. However, our number of photons are not conserved. That means if a light falls on the metal surface, the electron kicks out, then the photon goes off. Why? Because energies are being absorbed. So It means that the metal surface absorbs light energy. The absorption is not continuous. If it is a wave, it has to be a continuous. Since it is a particle, the absorption of a light by a metal surface is not, it is discontinuous, it is discrete. Alright, it is discrete. So this is what we talk about, right? So this is these points. I've done 5 different points. All this point tells that light has particle natures. Light has particle natures. Alright. So this is what we talk. Now we say that light has, therefore now I have to say that no doubt light has wave nature and light has particle natures. So in a way I say that now light has what we call as a dual natures. What we call as now light has what we call as a dual natures. Alright. And then when you talk about a particle, we say that it has a definite inertia and definite momentum. That you should keep in mind. Alright. So this is what we do. And Einstein photoelectric equations could have explained all the photoelectric equation or photoelectric phenomena, right? Photoelectric emissions, right? All the emissions could be able to explain by Einstein equations. So therefore, because of this work, he was awarded Nobel Prize in the year maybe in 1920 or something like that, right? So with this we come to an end of what we call as a dual nature of light. And now next we will talk about dual nature of matter. Thank you.